Good morning, everyone. It's a pleasure to be here for the first edition of VOMS. Today, I'm going to talk about architecting persistent memory systems, and more specifically, I'll be talking about how can we achieve the maximum possible performance out of these systems. Uh, Before I begin, I'd like to acknowledge my supervisors Vijay and Stratus and my collaborator Marcelo, with whom I've done all of the work that I'm going to present today. So let's begin by first understanding what is persistent memory. So if we look at the memory hierarchy landscape, here on the y-axis I'm showing access granularity, and on the x-axis I'm showing access latency. So if you look at a traditional computer system, we have volatile caches and DRAM, and by volatile I mean if you switch off power, it will lose the data that is stored in those devices. And then at the far end of the latency spectrum, you have this non-volatile medium, which is secondary storage. It can be hard disks, solid state drives, and whatnot. Now, there are a few key differences apart from them being volatile and non-volatile. Another important difference is the latency. So if you look at caches and DRAM, they have relatively low latency and are considered closer to the processor, whereas secondary storage has orders of magnitude higher latency. And another difference is that caches and DRAM can be updated or modified at a very fine granularity, which is typically a cache line. Whereas for secondary storage, updates happen at a much coarser granularity, which can be a block or a page. On this landscape, a new kind of memory is emerging, known as persistent memory or non-volatile memory, NVM. Now, there are multiple technologies that can be used to realize this kind of memory, but the key takeaway is that this memory has access latency and access granularity characteristics similar to DRAM, but it provides the benefit of being non-volatile. So even if you switch off power, you can still retain data in these devices. So essentially, non-volatile memory provides you with fast, fine-grained persistence. Now, if we look at a traditional computer system, which is on the left here, we have cores, caches, and DRAM, which are all volatile, and then you have secondary storage, which is non-volatile. With the emergence of this non-volatile memory technology, you have cores and caches which are volatile, but then you have, at the memory level, you have this non-volatile memory, which can retain data when you lose power. For the sake of simplicity, I'm not showing DRAM here, but you can have NVM and DRAM both sitting in parallel to each other or in some other configuration. Now, so this is great, right? So earlier, if I wanted to make any data persistent, I had to go all the way to secondary storage, which had a very long latency. But now I can do it at roughly the memory latency. So this emerging system, if I use this system and all the applications that require persistence or that require data to be stored in a non-volatile medium, they should magically run faster because I have this memory which has very low access latency. And if I just do this, ideally, my problem is solved and I can just pack my bags and go home. But as is usually the case, it's not that simple. Now, if you look at this picture closely, the boundary between volatile and non-volatile memory in a traditional system is software controlled. So whenever you want to move data or typically pages from between DRAM and secondary storage, the software or the operating system is involved in the process. That is why it has complete control and information about what data is moving from volatile to persistent domain. But if you look at this boundary in this emerging system with NVM, the boundary between volatile cache and non-volatile memory is hardware controlled. So the software does not have complete control or information about when data is going to move from volatile to persistent domain. And this is a problem. But just to summarize, what is persistent memory? It is a great opportunity to unify memory and storage, which allows access to persistent data through the processor load store interface, which has really low latency. But it has a challenge of maintaining consistency of data structures in persistent memory. And that challenge arises because the boundary, as we saw in the previous slide, is hardware controlled. And we need primitives to ensure that we retain a consistent state of data structures in persistent memory. Let's understand this. We'll understand this problem in more detail. But before, so as part of this talk, I'll talk about two key primitives that are used to ensure consistency of data structures. One is ordering persist operations and another is atomic durability. And then we'll look at how we can combine these two to provide fast checkpointing of applications, and finally I conclude. So now let's understand this consistency problem in a little more detail with this example. So here what I have is a linked list. Here at the top I am showing the cache, which is volatile, and at the bottom there's NVM, which is non-volatile. Now if I want to add a new node to this linked list, here is what I would do. I would first create a node, and then I'll update the node pointer to point to the existing head of the linked list. And finally, I'll update the head pointer to point to the new node. Now, as you would have noticed, some of the updates that happened in the cache trickle down to NVM, but not all of them. So the update to node pointer has not reached NVM at this point of time. And this happens because the hardware can flush cache lines from the cache in any arbitrary order. So if my system were to crash at this point of time, if I were to, let's say, suddenly lose power, I would lose all the data in the cache, and the data that I have in my non-volatile memory is essentially inconsistent. It is not usable. So how do I solve this problem? So if I want to solve this problem, here is one way. So after creating the node and updating the node pointer, I would insert what is called a persist barrier. This is similar to fences that are used for ensuring visibility. What this persist barrier guarantees is that all the updates that happened before the persist barrier would reach non-volatile memory before any update that happens after the persist barrier. So here, because of the persist barrier, when I update the head pointer, the data structure in NVM will always be in a consistent state. And this mechanism of using persist barrier is essentially dividing my program into two parts, which we call epochs, epoch A and epoch B, by using this programmer introduced persist barrier. And this division of program execution into separate epochs is known as epoch persistence. We'll understand this more in the next slide. So in order to guarantee consistency, in processors we have memory consistency models. Similarly, to guarantee consistency of data structures in non-volatile memory, we have what is known as persistency models. Now, these models reason about the order in which updates to various data structures reach a non-volatile domain, which is NVM in this case. This is similar to memory consistency models, which reason about order in which stores become visible. Now, a few models have been proposed in the literature. I'll not go into detail into all of these models, but just to briefly introduce them. So there's something known as native or strict persistence. This model follows the relevant memory consistency model of the processor. So if your processor is sequentially consistent, which means all the stores need to be ordered, then this model will ensure that after any update, any to update will always reach persistent memory in the program order. The second model is epoch persistence, for which we saw an example just a couple of slides before. Here, the ordering relation in native or strict persistency, the ordering relation was tied to the memory consistency model. In epoch persistency, the ordering relation is not tied to the memory consistency model, but it is relaxed in the sense that you can have a group of stores and guarantee that groups will persist in order. And in some sense, this is similar to the relaxed memory consistency models. And finally, there is strand persistency, which allows some epochs to happen in parallel and order some of them, but we'll not go into detail of that model. So with these persistency models, there is a question of how do you actually go ahead and implement these models. So there are two ways in which you can implement these models. One is non-buffered and another is buffered. In the non-buffered implementation, whatever persistency model you want to guarantee is enforced synchronously. So let's say if I want to guarantee epoch persistency, after I complete executing an epoch, I will first flush all the data that has been modified in that epoch to non-volatile memory and then proceed executing the subsequent epoch. These models can be implemented using instructions provided by various architectures like Intel and ARM, and But the problem is that they enforce these ordering constraints sequentially, which degrades program execution. And we'll look at that with an example later on. Another way of implementing these models is what is known as buffered implementation. In a buffered implementation, the ordering is enforced not synchronously but asynchronously, in the sense that you enable the memory hierarchy in the processor to keep track of relevant order that needs to be enforced and allow it to enforce it in the background. So your program execution can continue executing various epochs that need to be ordered, but they don't wait for each epoch to be flushed to NVM before executing the next epoch. And there are a lot of proposals have been made for these kinds of buffered persistency models, primarily because they provide higher performance. So let's look at a non-buffered persistency model. So here at the top, I'm showing visibility, which means whenever a processor executes a store, that store will be shown at the top. And at the bottom, I'll be showing persistence, which is whenever a store reaches a persistent medium or non-volatile memory, it will be shown at the bottom. So let us look at a sequence of stores in a typical program. We are primarily interested only in stores because persistency models reason only about the order in which stores happen. So let's say we have the sequence of stores that need to be executed. And here we can see that they will be visible in the program order. And while the program is executing, some of these can get replaced from the cache to a non-volatile storage medium. At the end of the epoch, you will have persist barrier. Since this is non-buffered epoch persistence, this epoch will first be flushed. So any data that is modified as part of this epoch will be first flushed to non-volatile memory, and only then the processor will start executing the next epoch. And so on. When the next epoch ends, again, all the data modified in that epoch will be flushed and it will execute a subsequent epoch. But here you can see that persist operations are happening in the critical path of execution, which will slow down your program, which will increase your program execution time. So to mitigate this, a mechanism called to mitigate this, buffered epoch persistence models have been proposed. And instead of persist barrier, let's call it lazy barrier, primarily because it is going to enforce those ordering constraints lazily in the background. It's an implementation of epoch persistence where durability lags visibility. So program execution can continue beyond epoch boundaries without waiting for epochs to actually persist. And thus, the hypothesis here is that you will allow epochs to persist out of the critical path of program execution, or in other words, without slowing down your program execution. So let us look at the same example, but with buffered epoch persistence. Now, after executing first epoch, since this is buffered, you can start executing the next epoch. But as an implementation of this model, you would make the memory hierarchy in your processor aware of which cache lines belong to which epoch and the order that needs to be enforced across epochs. So, and like before, you can have random cache line evictions as long as they do not violate epoch order. So if we go on executing like this, then we encounter something known as epoch conflicts. Now, what is a conflict? If you see here in epoch 3, we are trying to modify cache line D, which has already been modified in epoch 2, but it has not been persisted yet, or it has not been returned to NVM yet. Now, if we allow this store to complete without persisting the previous epoch, my data in NVM is going to be in an inconsistent state, and if I lose power at that point of time, I'll end up with inconsistent data structures. So, as we can see, these conflicts bring persist operations back in the critical path. The hypothesis with buffered models was that since you have it buffered and you can enforce these ordering in the background, you will not have these happening in the critical path and your program performance will improve. But because of these conflicts, persist operations come back in the critical path of program execution. So what we saw here is what is known as an intra-thread conflict. So here I'm showing epochs belonging to a single thread. I have not looked at a multi-threading example as yet. And in order to overcome this, we have proposed something known as a proactive flush. Now, if you look at persist triggers in the lazy barrier implementation that we saw previously, it's either a passive trigger, which is random cache line evictions happening in the relevant epoch order, or it's a reactive trigger, which is whenever you encounter a conflict, that is when you start flushing cache lines to NVM. And because of these kinds of triggers, persist operations end up in the critical path and degrade your program execution time. To overcome this, we propose a proactive flush, which uses a proactive trigger. Essentially, what we are saying is that proactively start flushing epochs whenever they complete, so that you reduce the probability of encountering conflicts in the future. So let's look at the same example, but with proactive flush this time. So after executing epoch 1, the program starts executing epoch 2, but the memory hierarchy in the background will start flushing whatever was modified in the previous completed epoch. And subsequently, when it executes epoch 3, since it would have already flushed cache line D, which belonged to epoch 2, we don't encounter the conflict again. Thus, this proactive flush mechanism helps us eliminate these intra-thread ordering constraints. Rather, it helps us reduce the probability of encountering these ordering constraints. Similar to the intra-thread conflict, a similar conflict can happen between two threads. So if there are epochs in two different threads which are trying to modify the same cache line, we can still have these conflicts happening. Now, with the existing lazy barrier implementations, there's no tracking of inter-thread dependencies. And hence, again, if you have an inter-thread conflicts, flushes or writes to persistent memory will end up in the critical path, and you'll end up with the same problem. So to overcome this, multiple mechanisms have been proposed. I'm just mentioning one here, but the essential idea is, along with the ability to track dependencies within a thread, the ability to track dependencies across threads is also important, and it should be provided in any buffered persistency model that is implemented. I'll not go into the details of this inter-thread mechanism, but let's look at some of the evaluation results. So what we'll see is a lazy barrier which has these conflict problems, both inter-thread and intra-thread. Then we'll look at lazy barrier with the proactive flush mechanism. And finally, we'll look at LB++, which is the lazy barrier which implements both the proactive flush mechanism and also a mitigation technique to ensure that you correctly track inter-thread dependencies as well. So we evaluate a server class processor, which is a 32-core CMP with 32 1 megabyte LLC cache banks and 4 memory controllers. What we want to essentially measure is what is the performance of implementing buffered epoch persistency model in this processor. And we use it for maintaining in-memory persistent data structures. So we evaluate it on a set of micro benchmarks. These micro benchmarks are data structures which are typically used in applications that require persistence. So file systems, databases, etc. will use these data structures in some form or the other. So what we are showing here is the throughput, transaction throughput for these data structures normalized to the lazy barrier design, a design which does not implement any mitigation mechanisms for inter or intra-thread conflicts. So if you look at proactive flush, on an average, it provides a 15% improvement in throughput. Now, if you recall, the mechanism is very simple. You start flushing as soon as the epoch completes, and with a simple modification, you can get a good enough 15% improvement in performance. And if we use LB++, which implements both the proactive flush and the inter-thread dependency tracking mechanisms, you get a performance improvement of 22%. So this is really great. The key takeaway here is that buffered persistency models are good and are necessary, but we need to be careful while designing these models, and we need to be aware of these pitfalls which we can encounter in the form of conflicts that we saw. Next, let us look at atomic durability. So what is atomic durability? Atomic durability essentially guarantees that either all or nothing persists. You can think of it as ACID transactions that you would have read about in databases. So let's look at this with an example. So let's say we have this variables a and b whose initial state is 0, and we want to apply the following transformation on this initial state atomically. So if it were to be applied atomically, then the final state can either be both are 0 or both are 1, which means either the transformation was applied completely or it was not applied at all. We cannot have the intermediate states wherein one of them is 1 and the other is 0, which means you cannot have an incomplete update if you guarantee atomic durability. Now, what are the mechanisms used to guarantee atomic durability in systems? So there are primarily two classes of mechanisms. One is known as shadow paging and other is known as write-ahead logging. Shadow paging is typically used in file systems or in systems wherein you want to guarantee atomic durability at a very coarse granularity, so typically at a page level or at a block level. But if you want to guarantee atomic durability at a fine granularity, then write-ahead logging is used. Again, write-ahead logging can be implemented using either a redo log or an undo log. With a redo log, you have the read redirection problem, because whenever you are using a redo log, all the updates that you do within a transaction will be returned to a log. And if you want to subsequently read that update in the same transaction, you have to redirect yourself to that log, find that entry, and read the new value. The other mechanism is undo log, which does not have this read redirection problem, because all the updates that you do happen in place, but you also need to write undo log entries, which is the previous value of whatever you are trying to modify. And it has this problem of enforcing fine-grained log to data ordering. So let's understand undo log a little bit more. So if I were to implement a program or a transaction with undo log, I would do the following 3 steps. I would first compute, which is identify the data that I want to modify as part of transaction, which is A in this case. Then I would write a log entry which consists of the old value of that cache line along with the address of that cache line. So since the old value of that data is 0, I would write a log entry which says that, okay, cache line A, whose undo log entry has the value 0. And finally, I would go and modify that value in place. So if we see what essentially we need to do as part of undo log is, it's essentially a data movement operation. We need to move the old value of data from in place location to a specific log area. There is another property of undo logging which we'll understand with 2 examples here. So if we were to implement an undo log in a disk-based system, this is what we would typically do. So we would first compute whatever we want to modify, write an undo log entry for it, and then go on and modify that value. Now we'll do this for all the values that we want to modify as part of an atomically durable update. And finally, after completing that, we'll first flush the log and then flush the data to the non-volatile medium. Now this works great because you have separate volatile and persistence phases. So if you are using disk, even though it is slow, you can amortize the cost of writing all the log and data entries to the disk by having multiple transactions first execute their volatile phase and then merge all the updates that you need to send to the disk and send it as a single batch. So there is a clear separation of volatile and persistence phases which allows you to amortize the cost of writing to disk. But if you look at the same thing in a system with NVM, after computing and writing the undo log entry, we have to first flush the undo log entry to the non-volatile medium, and only then the value can be modified in place. Why is this the case? Because as we saw earlier, the boundary between volatile and persistence medium is hardware controlled. So if we don't flush this log before modifying the value in place, the modified value might get replaced from the cache and reach NVM. And again, if my system crashes at that point of time, I end up with an inconsistent state. So in systems with NVM, we need to enforce these fine-grained log to data ordering dependencies. So essentially with undo log, we have this benefit that it's a very simple data movement operation, but at the same time we need to be careful and we need to enforce these fine-grained log to data ordering dependencies. What we propose is Atom, wherein we want to move these log to data ordering dependencies and the data movement task of copying the log, copying the in place value to the log area out of the critical path and into the hardware, push it into the hardware, or more specifically, push it into the memory hierarchy. And how we do this? So let's first look at how can we have a baseline simple undo log mechanism in hardware. So let's say we again want to modify this value A. So the core will issue a store instruction saying that, okay, write 1 to this cache line A. Now cache, before modifying that value, will first write a log entry for that in the log area, which it already has the old value of that cache line. Once it gets an acknowledgement from the memory that the log write has completed, it can complete the store request from the processor. So the cache hierarchy easily implements this data movement task, and it uses this feedback mechanism to guarantee that log to data ordering is always enforced. But if you look at this, it's not great in terms of performance. So let's understand this better by looking at the latency breakdown for a single store. So here what we see is a store queue, which processors typically use to move stores out of the critical path of execution. Then the store queue talks to the cache hierarchy, which in turn talks to the memory controller, which finally writes value to the memory. So let's say the store queue issues a request saying that store something to cache line A. When that request reaches the cache, it will first write the log entry, as we saw previously. The log entry request will go to the memory controller, which will write it to NVM. Finally, when the write is complete, the memory controller will acknowledge saying that the log write is complete to the cache, and the cache will complete the store request from the store queue. Now, if you look at this, store completion time includes this write latency to memory in the critical path. So each store request will have to go through this relatively long latency of writing to NVM, which will eventually fill up the store queue. So even though stores are out of the critical path of typical applications, if your application requires atomic durability, your store queue will fill up and it will stall the processor pipeline, thus again degrading the performance. So how do we solve this? So with Atom, we first propose what we call a posted log. So again, when the store queue issues a request, the request will go to the cache will send it to the memory controller, and the memory controller will issue a write to memory. But in parallel, without waiting for that write to complete, the memory controller will track address A saying that a log write for that particular cache line is pending, and it will send an posted acknowledgement back to the cache, and the cache will complete the store request. So in the meanwhile, if this cache line were to get replaced from the cache, it will reach the memory controller. But since the memory controller knows that log write for that cache line is pending, it will not write that cache line to NVM until that log write completes. So by doing this posted log write, we are able to reduce this store completion time. Now we can go a step further and do one more optimization. So what happens if you have a store miss in the cache? So I'm not showing the entire sequence of operations wherein the store request will go to the memory to first read that cache line back to the cache hierarchy, and then it will modify the value. So let's say the store request missed in the cache, and the cache sent a read request for that cache line to memory. When the read request completes, memory controller will send the value back to the cache. The cache will then issue a log write, because this is part of an atomically durable update, which will again go to the memory controller containing the same value that it read previously, write it to the issue a posted log write, and then complete the store request. Now if you see, store completion time has this unnecessary data movement from going from memory controller to the cache and back. What we can do is we can make the memory controller a little more intelligent to identify stores that can be logged at the memory controller level itself. So when the read request completes, first of all, if it's an atomically durable update, the read request that goes to the memory will say that, okay, this read request is for a store which is part of an atomic durable update, and that is why there's this read X. When that request completes, the memory controller will immediately issue a log write, because the old value that it needs to write for the log, it has just read that from memory. And it will send that value back to the cache saying that setting a bit saying that the log write has also been completed, and it will essentially complete the store request. So by doing this, we are able to eliminate redundant data movement between the memory controller and the cache hierarchy. So let us look at some results for this implementation. So the designs that we'll look at here is a baseline design, which we saw previously, wherein the write to NVM is in the critical path of completing a store request. Then we'll look at Atom, which is doing posted log writes to the memory controller. We'll look at Atom opt, which not only does posted log writes but also does source logging if the store request misses in the cache. And finally, we'll look at a non-atomic design, which does not implement any support for atomic durability. So essentially, it is in some sense it gives you an upper bound on the performance that you can achieve. Again, we evaluate a similar design, which is 32 core CMP with 32 LLC cache banks and 4 memory controllers. We see the same set of benchmarks, and we are going to see normalized throughput, where the throughput in this case is normalized to the baseline design, which has these writes to NVM in the critical path of completing a store request. So with Atom, which has posted log writes, we achieve an average performance improvement of 23%, and with Atom opt, we achieve an performance improvement of 27%. Again, the improvement of Atom opt will essentially depend on how many misses that you have, store misses that you have while you're executing your atomically durable update. But more importantly, the non-atomic design is within 11% of the Atom opt design. So by doing these simple modifications to the memory controller, by making it a little more intelligent, we can achieve performance which is very close to an ideal design. Finally, let's look at combining ordering and atomic durability. Now, there is a very important class of applications that require periodic checkpointing, because the application execution time is much longer as compared to the mean time to failure of devices that it is executing on. Now, we can combine ordering and atomicity to guarantee checkpointing of applications at epoch granularity, wherein we guarantee that epochs will persist in order. So a program execution is divided into epochs which will persist in order, and each epoch will persist atomically. So if there is a power failure at any point of time, we can recover by looking at the last persisted epoch and continue executing from there. We call this model bulk strict persistency, which combines buffered epoch persistency and atomicity. It's a stronger persistency model, similar to native or strict persistency, and it's in some sense similar to doing sequential consistency in bulk mode. So again, I'll not go into the exact implementation details. Let's look at some of the evaluation results. So what we are comparing here. So first we look at SB, which is the non-buffered epoch persistency model, which will essentially flush data in the critical path of execution, which is typically the case in traditional checkpointing designs. Then we look at combining this non-buffered epoch persistency with Atom, which guarantees atomic durability. And finally, we look at the lazy barrier design with all the optimizations for eliminating inter-thread and intra-thread dependencies. And again, we look at it combined with Atom. We evaluate a similar system as we saw before, and we essentially are looking at bulk strict persistency, which is to checkpoint applications. Now, the results here are normalized to a volatile execution, to an execution which does not care about atomic durability, which again is the best case performance that you can achieve. Now, if you use strict barrier, then it has a performance overhead of around 2.3x over a volatile execution where you don't worry about checkpointing. But if you provide support in the form of Atom to a strict barrier, then you can improve the performance or reduce the execution time by 59%. And if you use LB++ along with that, you can further reduce that performance to 35%. More specifically, we can achieve checkpointing of applications with only a 32% runtime overhead compared to a non-atomic design which does not guarantee checkpointing, which does not guarantee recovery in case of failure. So to conclude, persistent memory is a very useful device to improve application performance that require persistence or non-volatility, but it requires primitives. We looked at two primitives. We looked at buffered epoch persistency and atomic durability. But whenever we are implementing buffered models, we need to be careful and we need to be aware of handling conflicts which can degrade buffered models to non-buffered design. And we can see that by doing simple modifications, we can achieve 22% better performance than the state of the art. When we looked at atomic durability, we identified that atomic durability based on undo log is essentially a combination of data movement and fast and fine-grained dependencies between log and data writes to persistent memory. And we show that we can easily offload it to hardware by doing minor modifications to the cache hierarchy and more specifically to the memory controller. And by doing so, we can achieve performance which is within 11% of the optimal design. So, and finally, we saw that if you want to checkpoint applications, we can combine these two primitives and we can guarantee checkpointing of applications with a low 32% overhead. To end, I would like to discuss some of the areas that I am excited about. So, when we look at acid, like we saw it for atomic durability, it's a combination of atomic visibility and atomic durability. We saw support for atomic durability in the form of atom. There is existing support for atomic visibility in the form of hardware transactional memory. Now, can we combine these two primitives to guarantee a hardware implementation of ACID transactions? More specifically, can we look at these two not as a single unit, but two design points that need to come together to have a performance efficient ACID design and use two different mechanisms. So for atomic visibility, we use eager version management, which is similar to undo log. But for atomic durability, if you are combining it with HTM, you look at lazy version management to guarantee faster commits. If we can combine these two into a durable hardware transactional memory design, it will be great if we can also use the logging support to extend the transaction write set size beyond L1. The existing commercial HTM designs have their transaction size limited to either the L1 or some store queue data structure, some store queue design in the processor itself. Can we use some of these logging for durability to extend that write set size without adding additional hardware overhead? With this, I'd like to stop and thank you for your attention.